Hello and welcome to chemistry. I think you guys are going to like chapter 13, mostly because it's a little easier than chapter 12, 11, 10. Honestly, it's probably the easiest chapter since like chapter 5 or 4 or something like that. So it's a nice little break from all the crazy math. Chapter 14, though, we'll get right back into it. But for now, let's enjoy this little break we got going on here. So chapter 13, we're just learning about the states of matter. We're most of you probably know about like solid, gas, and liquid, and that will be brought up in this chapter. But we're really going to learn a lot of scientific terms to describe solids, liquids, and gases and why they act like that. So it's a little more in depth than probably what some of you are used to when we start talking about the states of matter. First up, let's talk about gases. Okay, so normally, no, let's just talk about gases. The kinetic molecular theory is one of the main theories that we need to explain everything in this chapter, specifically gases. If you look on the bottom of the page right there, it says the kinetic molecular theory describes the behavior of gases in terms of particles in motion. Okay? Particles in motion. So what we consider is them a bunch of little, the way I imagine it, is a bunch of little marbles flying around really fast everywhere. And by imagining them like that, we can apply some rules to them that give us a couple of the explanations for a couple of the characteristics that they have. So let's look at a couple key components of the kinetic molecular theory. We assume that there's particle size, particle motion, and particle energy. Gases consist of small particles that are separated from one another by empty space. The volume of the particles is small compared with the volume of the empty space. And because gas particles are far apart, there are no significant attractive or repulsive forces among them. So that's one of the assumptions we're making. There's actually quite a bit of information in there, but we're assuming all of that is true. That when these guys are flying around, they don't really interact with the other ones unless they happen to hit each other. But they probably won't because they're so far apart. Next up, we have particle motion. Gas particles are in constant random motion. Particles move in a straight line until they collide with other particles or with the walls. Collisions between gas particles are elastic, and an elastic collision is one in which no kinetic energy is lost. Kinetic energy can be transferred, but the total energy, but the total kinetic energy of the two particles does not change. Okay, so gases are always moving around like crazy, always bumping into things. They're always just going to move in a straight line until they hit something, and when they do, none of that energy is going to be lost. They're just going to transfer it somewhere else, whether that be right back to themselves in the form of a bounce, or maybe they'll just deliver all their energy to another particle, and that particle will kind of steal that energy. In either way, the energy doesn't disappear, it just gets transferred. We also have to consider particle energy. Two factors determine the kinetic energy of a particle, and that's the particle's mass and the particle's velocity. We see here that Ke, representing kinetic energy, is 1/2 mv squared. M being the mass of the particle, v being the speed of the particle, or velocity. The difference between velocity and speed is that velocity, you're talking about a direction. Speed, you're not. Speed, you're just talking about how fast. But velocity is saying how fast in what direction. So if you're going 30 miles an hour, that's a speed. If you're going 30 miles an hour east, that's a velocity. So in a sample of any type of gas, all particles have the same mass. So let's say this up here, all these are the same type of gas, so they have the same type of mass. But not all of them are moving around at the same speed, which means they don't all have the same kinetic energy because this velocity is not the same for all of them. Okay? But if we added up all of the kinetic energies of each one of these little particles, if we added up all of those, we would get what we call temperature, which is just a measure of the average kinetic energy of the particles in a sample of matter. You might not have heard temperature described that way, but that's all it is. We just take the average kinetic energy of all the particles, and that's what temperature is. So if these guys are flying around a lot faster, then we increase the kinetic energy, so that might increase the temperature. So by taking this theory to heart, I don't know why I said that. By taking this theory and applying it, we can hopefully explain some of the behaviors of gases. For example, the constant motion of gas particles allow a gas to expand until it fills its container. If you think of like a balloon, no matter how much air you put in there, it's full of air, right? Like the balloon can stretch. I'm not arguing the balloon can't stretch, but if you blow a balloon for like 10 seconds or 20 seconds, either way, you would say the balloon is full of air. And that's because of these properties. It can expand until it fills its container. If you just have an empty water bottle and you put the lid on it, you would say it's full of air because the gas has gone in there and filled it up. So gases are extremely low density. Remember that density is mass per unit of volume. So how much stuff fits in a given amount of space? Chlorine, gas, is 2.95 times 10 to the negative third grams per milliliter. That's not very much. And that's at 20 degrees Celsius. However, solid gold is 19.3 grams per milliliter. You can see that those two numbers are very different. This is 10 to the negative third, and this is 19. So this is way bigger. In fact, it says right here, 6,500 times more dense than chlorine gas. Now, yes, gold atoms are bigger than chlorine gas, but not that much bigger. Okay, so what's happening here is that there must be a bunch of empty space in the chlorine gas. Does that make sense? If you have a jar of gold and a jar of chlorine gas, the chlorine gas is going to weigh less because there's a lot more nothing inside of it. There's a lot more empty space inside of it compared to a solid chunk of gold. So gases have very low density. Gases can be compressed or expanded. It gives a little example here. If you squeeze a pillow made of foam, you know you can compress it. That's because it shoots out all the air. Well, in the same way, if you can compress a gas, you're essentially squishing all the particles closer together. When you stop squeezing, the random motion of air particles fills the available space and the pillow expands to its original shape. Figure 13.3, which is over here, illustrates what happens to the density of a gas in a container as it's compressed and allowed to expand, so back and forth. So if this is normal gas and we compress it like we were talking about, notice that there's a lot more stuff in a smaller amount of space. Right? Let me rephrase that. There's the same amount of stuff in a smaller amount of space. They have the same amount of particles, but up here, it's in a smaller amount of space. This is more dense. If we go the other way around, if we expand it, these now have the same amount of particles, but this has a lot more empty space, so this is less dense because there's less stuff per total volume. Okay, so up until this point, you guys are probably with me. You guys probably learned all this stuff before. If not, you probably have some intuitive sense. These two are kind of the two new things in this chapter. So according to the theory that we were talking about, there's no significant forces of attraction between the gas particles, which means the gas particles can fly next to each other and nothing's going to really happen to them. Often, the space into which a gas flows is already occupied by another gas. So like if you spray perfume, that's a gas, and it's going into another gas, which is just the air. The random motion of the gas particles causes the gases to mix until they are evenly distributed. Diffusion is the term used to describe the movement of one material through another. Let's go ahead and do this. So here, let's say we have, this is air, and then we spray some perfume over here. If we remove the divider, we know that eventually this stuff will spread out evenly. So if this red stuff is a perfume, it was a lot stronger over here, but if we give it enough time, the perfume will make its way over there, and we will give it enough time. The rate of diffusion depends mainly on the mass of the particles involved. Lighter particles diffuse more rapidly than heavier particles, and that's because of that equation of kinetic energy. for lighter particles to have the same average kinetic energy as heavier particles, they have to be moving a lot faster because the equation uses both mass and velocity. So if you have a small mass, you have to have a big velocity. You can see right about now, everything's kind of even. If we look at the center mass is right there. So it's pretty much spread out. So if you spray perfume over here, and then the red stuff expanded, now the perfume is everywhere in the room, and that's an example of diffusion. Now let's look at effusion. It's pretty related, but it's specifically when a gas escapes through a tiny opening. So like if you have a balloon and you don't pop it, but there's just like a leak, that's what we're talking about, effusion. Or if you have a big jug of something and you just open the lid, that's effusion. So this guy, Thomas Graham, did experiments to measure different rates of effusion for different gases at the same temperature. And Graham designed his experiment so that the gases effused into a vacuum, which means into a bunch of nothing, a space containing no matter, not even air. He discovered this relationship. The rate is inversely proportional to the square root of its molar mass. Okay? Graham's law also applies to rates of diffusion, which is logical because heavier particles diffuse more slowly than lighter particles. Using Graham's law, you can set up a proportion to compare the diffusion rates for two gases. So in this class, we're not going to find the actual rate, just a little above our heads, but we can find out like if one gas will release all of its stuff faster than another one. So if we have two jars of these chemicals and we open them up, we can compare which one of them will allow more material to leave faster. Essentially, which one will evaporate faster is the way you can think about it. Here we can see a picture of what we're talking about. These two things, we can compare which one of these will effuse faster than the other. Or diffuse faster, I should say, because it's going through the air. But in order to do that, all you need is the molar mass, and then you can find out which one is faster. So notice here, we never plugged in anything for the rate. It's just the molar mass of one divided by the molar mass of the other. Take the square root, and we get 1.47. Okay, so 1.5, we can say 1.5. So we can say this one, ammonia, diffuses 1.5 times faster than HCl. See how we read that? We read this top one, this, and then the bottom. Although something you do want to point out, or I do want to point out, the rate of NH3, and then the molar mass of NH3 is on the bottom over here. You see that? So NH3 is on the top over here, but NH3 is on the bottom over there. Look out for that as well. So talking about these things hitting different things, you have a bunch of little particles inside of a container that's hitting the inside of the container. And this gives us what we call pressure. The book gives the example of walking across snow. If you're just wearing regular shoes, you're going to put your foot right through the snow, but if you have snow boots on, or snowshoes, I should say, the snowshoes spread out the pressure, the area in which you are applying the pressure, applying that force. And because of that, there's less pressure, so you won't go flying, your foot won't go through the snow. It'll get to stay on top. That's what we see here. It distributes the force over a given area, and that lowers the pressure. So pressure is defined as force per unit area. It's the same way why if you lean on a wooden table, nothing happens. But if you lean on a sharp pencil with the same amount of force, it's going to hurt because there's a lot more pressure in that one spot. Okay? So gas particles exert pressure when they collide with the walls of their container. Because an individual gas particle has little mass, so since each one of those has very little mass, it can exert very little pressure. However, there's a lot of gas particles in a container. We see here there's 10 to the 22nd amount of gas particles in a liter of gas. Okay, so one of them isn't really doing much, but the fact that we have this many particles, each contributing a very small amount, means that the pressure is actually measurable. right now, you might not know it, but you are being squished by an atmospheric pressure. There's all sorts of gas particles smacking you in the face right now. That's giving it pressure. It's the same reason why water is not just one of the reasons why water is not just evaporating if you have a glass of water open right now, because that water is being pushed down by the atmospheric pressure just a little bit. The higher you go, like up to the mountains, the less pressure there is because there's less stuff on top of you. Does that make sense? If you're in the bottom of a valley, there's a lot more air on top of you squishing you than if you were at the top of a mountain. There's a couple ways to measure this air pressure. A barometer and a manometer. Here we see them. So here, there's a tube of mercury, a tube filled with mercury, liquid mercury, with a vacuum on the top, which means there's no air in here. And the mercury will be pulled down by its own gravity. But because of this container, there's air in it pushing the mercury up. And that pressure is the same thing as the atmospheric pressure. So atmospheric pressure is pushing down on this thing, which is pushing the air up here, which is trying to balance out with this, with the weight of the mercury. Because of that, it will always line up to a certain point. If the air pressure increases, then this mercury will go up because this is pushing this up and the force is stronger. So it'll force all the mercury to go back up. Or if there's a low atmospheric pressure, then mercury can push down on the air easier and this will be open a little bit more. This is called a barometer. We measure that in terms of millimeters of mercury. We don't need to really worry about that, but as this increases the pressure, this pushes the mercury up. So we see that right here, the mercury goes up. A couple ways to measure pressure. You guys might have heard of PSI, pounds per square inch. A lot of engineers and stuff use that still. I'm sorry. There's other units like millimeters of mercury, as we were talking about, kilopascals, pascals, torr, atmosphere. Out of all of the things we are measuring, atmosphere and pressure is the one that is probably the least standardized. So you know, like meters or kilometers and meters and stuff are the international units for distance. Well, pascals are the units that scientists use, but the other ones are still used quite a bit. 1 Pascal is equal to a force of 1 Newton per square meter. Engineers use PSI, as we said before. If you just have a little barometer at home, you're probably measuring in millimeters of Hg. Also might be called torr. Typically, the average atmospheric pressure is 1 atm. So at sea level, the average air pressure is 760 millimeters of mercury when the temperature is 0 degrees Celsius. That's important. Okay, so we get all these crazy conversion factors, hint, hint, for later chapters, where 1 atmosphere is equal to 760 millimeters of Hg, or 1 atmosphere is equal to 760 torr, or 1 atmosphere is equal to 101.3 kilopascals. Okay, so we just got a bunch of conversion factors there that we will use in later chapters, being able to relate these different types of atmospheres, or different types of pressures, I'm sorry. One more interesting thing about these gases is that if you have this gas and this gas, each under different pressure, and you combine them, luckily this is easy. Their total pressure is just the one pressure plus the other one. So what that essentially means is that the gases exert pressure independent of what the other gases are doing. And this is Dalton's law of partial pressure. The total pressure of a mixture of gases is equal to the sum of the pressures of all the gases in the mixture. Really straightforward. That just means if you want the total pressure involved, you just add up all of the pressures of the smaller gases that you put in there, the component gases that you put in there. For example, we see that if we mix this particular mixture of oxygen, CO2, and nitrogen has a total pressure of 0.97. Okay, and then it says the partial pressure of CO2 is 0.7, partial pressure of N2 is 0.12, so what's the partial pressure of O2? Well, this is easy. We know that the 3 added up equals 0.97, So we just have to subtract the other two from our total, and we get our answer. Super simple. Super simple. In this case, if we were splitting up water into hydrogen and oxygen, and we emptied the gas out into a specific chamber that's 20 degrees Celsius, we know the pressure of those gases at those particular temperatures. Okay, so then we could use that to maybe mix with some other gas, and the difference is the pressure of that gas rather than the O2 or the H2, because if you added up all of their gases, all of their pressures of each gas, you get the total pressure. And that's about it for 13.1.